All right, one more Hoon school here. I sent an email and I was kind of talking about our big concept being cores. That is true. Um, what we're going to talk about tonight bears the name subject-oriented programming. I'm going to contextualize a little bit what that means in terms of programming paradigms and what we're trying to do with Hoon. What Hoon is trying to do as a consequence of compiling to Nock. But in terms of the effort expenditure that you're going to have working on Hoon, this is going to be the biggest payoff idea that you'll deal with. Essentially, understanding core nature is really one of the bright line ideas. And I think anyone can understand it, no matter what language background or not, or programming background or not you have. But this is the place to focus your energy. This is the thing to understand. The rest of it, we've been talking about syntax. We've talked about like bare values as atoms and cells and stuff. I think that sort of stuff you've probably got down at this point. But cells are this unifying golden thread that runs through all of Hoon. And you're going to run into them in all sorts of unexpected places. And they allow you to do lots of things that are, powerful, right? The things that Hoon lets you do, even where they're analogous to other programming languages like functions. Hoon has gates and traps are both like functions in some ways. I guess traps are more like loops in the current terminology that we're using. But cores are going to organize all of this into one overarching concept that is extremely general, extremely powerful, and it's going to take you a couple weeks to really wrap your head around getting deep into what cores look like. To start us off, let me pop over to a shared screen and get Zoom out of the way. Okay, come on. All right. So before we talk about any Hoon in particular here, classically, we can kind of talk about different programming styles, different ways of organizing code. To some extent, people think of these as being characteristic of particular programming languages, although to some extent, you can implement most of these in most programming languages. But they're kind of different emphases, kind of like playing in different keys in music. They give it a different feel. Probably the most common way of thinking about this is imperative programming. And imperative programming is focused on control flow. It's more like a recipe. It's a way of organizing and structuring what you are telling the machine to do very explicitly and how you are expecting it to carry out those commands. So it tends to be a series of commands. So a script or a C program, a lot of JavaScript, these things tend to look like this. Another way of creating a computer program is to do what's called declarative, which focuses on data flow instead. Databases are like this. To some extent, Excel is somewhat like this, where you're talking about, there's a relationship between certain cells, but what you're really thinking about is the way that information flows from one place to another. And the details of the operations are often sort of glossed over for you. You're just telling Excel, do a VLOOKUP, and it goes and it does a tabular lookup, and you don't worry so much about the details of that. Databases are like that as well. You're telling it to locate a bit of information. You don't care how it locates it. You care that it accomplishes this. Functional programming is kind of a subset of declarative programming, but it's important enough that it gets its own category here, and it focuses on composition of functions and expressions in kind of a mathematical sense. And you can do it in other programming languages, but it tends to be characteristic of languages like Haskell or APL or OCaml. And it's very much, you're just talking about how does one function apply to the next, and sort of how do these things build up together. And then the other major one that you see, to the extent that these don't have some overlap, which is natural, is object-oriented, which focuses on relationships between different entities, between entities containing data and code. This is common with window managers, for instance, where you have a dialog box and it needs to send a message to the window in the background so the information gets properly updated. A lot of video games are heavily object oriented because you can represent a monster or something, an entity as a thing. It has its own data and code associated with it, but it needs to pass messages to other entities to get them to work around. Hoon is going to be situated in a paradigm called subject-oriented programming. It has some commonalities with functional and object-oriented programming. You could think of Hoon in some ways as a functional language with very strict scoping rules. If I lost you here, that's okay. We'll come back to this point as we keep working on this. But essentially, any Hoon expression resolves against the binary tree that spawned it. So we've kind of been emphasizing this idea that all of Hoon, all of Urbit is literally a binary tree. It is a noun. It contains atoms and it contains cells. And so when I do something, this might be foolhardy because I don't know what else in my subject right now. Yeah, so it's going to grind on that for a second. If you have a fresh fake sod, this will work fine. If you have an old fake sod like mine and there's a lot of junk in your subject, it might not work so well. You can do Control-C to pause the evaluation. If I do something like add, then the right-hand side of this is basically the subject that add sees, which we'll come back to, a point we'll come back to in a moment. So add sees something about Hoon version 139, and it's aware of some other things, 33 other arms that were defined at the same time, other parts of the binary tree that it sees are visible to it. So subject-oriented programming means that this horizon of visibility is all you really have to take into account in order to uniquely mathematically resolve the expression that was generated in Nock. Now, when we talk about binary trees, we started playing around with some wing resolution last week and the week before, and there were some questions about, what's the difference between colon and dot, which incidentally actually led me to write up at least I can find this thing. This hasn't been merged into the docs yet, but I did write up the difference between col and dot in terms of the underlying Nock operators that they let you access. But if we have some kind of expression that lets us define some Hoon here, so we have A's and B's nested inside of each other. So we've defined this data, then we can resolve things against this data. So I can say, A resolved within data gives me access to everything that has the face A attached to it. So it gives me this particular cell. And of course, within that, I can resolve another A and so forth. And in some respects, I can drop a colon, and the underlying Nock execution is a little bit different, but it'll still give me a functional expression in terms of what's going on here. And I can navigate different ways, right? I don't have to navigate in terms of names. I could say, give me the head of data, which is just the cell A and not the cell B. The cell B is left off because that is the tail of data. And so I can do positional notation within this. So when an expression like this actually resolves, right, the way that Hoon evaluates this, and we're going to get to cores in a moment, Hoon doesn't know whether or not a particular value is a face or an arm name until it conducts a search looking for a name, okay? So if I talk about data, then data is a name, it's a face that I attach to this particular instance in my subject. So in my dojo, as long as I'm working in my dojo, if I refer to data, it looks for the most recent definition of data, and then it matches that. So you can think of names as kind of a breadcrumbs. They're kind of a search path back to what's going on. So address-based search paths like head, and tail are always going to return your value as data. This is subtly different because when you do a name-based search path like add, it can actually give you executable code. If I were to figure out what the actual path of add is in my current subject and evaluate it, I wouldn't be able to get this back as executable code by default. Since data and code are interchangeable in Hoon, that's a very subtle difference, but that's the reason we use names for functions. Well, we're humans, we're mortals, right? We don't like to refer to addresses to invoke particular functions, but from the computer's perspective, we use names to refer to it because that gives us executable code back. Now, one of the interesting things is that we aren't restricted from reusing names. What was C supposed to be here? I don't know what I meant by C. Let's just say C equals 45. Let me go back to that expression. Okay. So you'll have to define some value of C for that to resolve. All right, so when I refer to double, double resolves against the subject on the right-hand side. So it looks up within this tree to the right-hand side, it looks up double. And if I were to refer to something that is known generally, but not inside of the right-hand side, like add can't resolve within that cell on the right-hand side, which, kind of makes sense. Now, if I were to define something interesting like this, with two things named double, this is something that an imperative or declarative programming language. So an imperative programming language would either error out at having two names within the same structure, the same cell in this case, or it would simply overwrite the first one with the second one. A declarative language would probably just overwrite the first one with the second one. So double 456 would be our match here. All right, so if I want to resolve double against the right-hand side, let's see what Hoon does. Okay, so Hoon matches, it searches and it finds the first thing that matches the name double, and then it matches that. One of the interesting things that's a consequence of subject-oriented programming is that I can resolve any name or address within my subject. So if my right-hand side here is my subject, I can tell Hoon with a ket to skip the first match and give me the second match. So both of these exist and they both have the same name, and I can access both of them. I just have to be specific about which one I'm accessing when I do this. So we can play some interesting games. It's not really common to do this, except that it's very common in functions to call, like if you have an input list, to just call it list. And then when you talk about list, you're no longer talking about the type, you're talking about the particular list that you have. And so if you wanted to talk about the type list, you would have to do ket list to skip that match. You'd have to look up one, which, might mess with you a little bit until you think about it some, but it does in fact work. Now, another part of Hoon, prefatory to us getting deeper into cores, is talking about gate building gates. Okay, so if I talk about something like add 1, 2, if I'm actually talking about add, then I can look at add and I can see that it has this description here of whatever the pretty printer decided to do with it. We know how to interpret this part, right? What is this part? If you're a fast typer, you can type or you can think about it, but like what is this part? What did we call this before? What does this represent? Right. So these are our arguments, right? We called it a sample, but essentially, yeah, these are the arguments. These are the inputs to add. What are these other two things? So when we went back to talk about cores, we said that they're always going to be a cell of battery and payload. All right. And I think at the time, I expanded that payload is going to be a cell of sample and context. So let's kind of work on this. So your battery is going to be your executable code, right? The actual knock code that gets evaluated. Since this is a cell, I can take the head of a cell. So I can look at the head of add, and I can see what add evaluates to. So in my current system, add evaluates to this operation in knock. Now it's mixed. Okay, so if I know knock, which you probably don't, you probably have never really looked at knock before other than incidentally, then I can recognize some of these rules as being, you know, an if else statement, or like knock 9 is a lookup. That's what a call does. So this code here, this expression here is actually saying, you know, we're going to go look up something that's in our current subject, and then we're going to replace it with that code. So it's not like fully the code that would execute with add, because part of it's a lookup of other code, but it kind of gives you the idea that add is knock code, right? That it exists as knock code. So this is the battery. If we look at the battery of any function like decrement, we can see what that value actually is, right? So that was a hep col dec, the head of decrement. You'll recall that decrement simply takes the value down by 1. The head of decrement is that knock code that just scrolled up over my screen there. Yeah, so not super long, but it doesn't fit on one screen the way I had things configured there. So that's your battery, that's your executable code. Now, one of the consequences of this is that when we define, we define a gate using a bar-tiz. This is something we've done a couple of times now. Called it function, call it a gate, whatever we want to call it. We've defined them before. And when we actually use them, the code that we want to use is essentially being built having had the sample values, the real sample values supplied to it. So last time, I believe Jack talked about this part, about gate building gates. Is that right, Jack? Was that part of yours? We have this idea.
We discussed like list being, list is a gate which takes a mold and returns a mold, but molds themselves are gates. So that is an example of a gate build.
Yes. So gate building gates are really important. And it turns out that anytime Hoon runs code, it's actually essentially doing that. It's building the code out of the gate that it needs to evaluate at that moment. So if I were to define an arm in place, let's do something like inc, which would be, you know, the opposite of dec. I'm going to add 1 to a value. In this case, get 6. So the code that I get from inc, for the most part, looks fairly straightforward, except for that rule 9 lookup again. Any large value tends to be a lookup. So it's looking up the value of add in its current subject. Those of you who remember the statement that we had before, which you probably know, unless you're following along in your terminal, may see that the address here is a different address. There's a different place we're looking at, because inc sees a different subject than decrement, than dec. It's in a different place in the binary tree, so it sees a different subject. It would look at its address would be a different lookup, relative lookup compared to where it is. So when we actually evaluate a gate, it pulls all the parts together and it builds the gate on demand. So we said last time that gate building gates are an extremely common pattern in Hoon. And it turns out that we're actually doing these all the time. Let me give you a long block of code there. Your best bet for copying that is probably use the 3 dots at the right of the chat to copy it. And it should preserve double spaces there in that case. All right, so this is a core, it's a bar sen. So what this is going to do is it's going to modify values by building gates. And so whenever I invoke something like add 10 resolved within C, and I give it a value, it's going to build the particular gate that I need and then return this value back to me. So I locate it inside of the subject, the core C with coal limb resolution. And then I use that to, Hoon uses that to build the gate given the actual value 50 that I'm supplying to it. So that's what's going on inside of the battery. Whenever I work with the battery, it's building the code that I want. Okay, so this is part of core nature, is that when I have an executable core like this with executable code, it is getting built on demand and then run for me. We'll do more with this, but this is kind of your entry into this particular aspect of that subject. So gate building gates are common sign pattern in him. All right. Now we have a payload, and I said that a payload consists of sample and context, right? So like what does that mean? So a payload is essentially the subject that the value sees. So Topsoil Phosphorus says, so gates are recompiled every time you call them. They're not necessarily recompiled because the system is smart enough to cache them. So you can cache prior builds, but you are very frequently using gates to build gates or building gates de novo when you evaluate them. Yes. So it's, I don't know if the technically accurate way would be to say gates are recompiled every time you use them, but the code that relies on the gate to specify it with the sample included has that sample injected as part of that evaluation / interpretation / compilation step. This gets a little bit fuzzier because we're kind of talking about a language that's kind of interpreted and kind of compiled in both senses here. If you've run into the difference between compiled and interpreted languages. So, all right. So the payload is the subject that the core sees. All right. And so it has a sample, which are input arguments, and has a context, which is the rest of the subject. All right. And most of the time, the context is just going to be the standard library. There are exceptions to this, but most of the time you're just assuming that your context is your standard library. That's all you're worrying about. So we can kind of ignore context until we start doing special things, which we will not even do in Hoon School. But you can see the different. Let's see. So if this is a cell, then +2 is our head. +1 is our entire thing. So let me do this with add. So +1 is our entire thing. +2 is our head. So this should be the not code. +3 is our payload, which should be everything on the right. So then there's no 4 or 5, but less. So that should be the input arguments as default. So if I change that to, for instance, mol, I can see the ones, the default ones that I specified. And the right-hand side should be the context. Most things see everything. So if I defined ink a moment ago, oh, good grief, it's going to evaluate with whatever's in my current. This is the problem with an old fake sod. An old fake sod gets a lot of things in it that are, so whenever you see, when you type something like this and you see it start to grind, you see the spinner there on the cursor, that means that whatever you're printing is large enough that the pretty printer is having to like reprocess and reformat everything. And most of the time it's not worth your while to try and wait for the pretty printer to print everything. So just Control-C out of it and throw it away. Let me try. Okay, so AP is a different core in the system. And if I do AP instead of add, you can see that it sees a different subject, because Hoon itself is defined as a set of cascading cores. So the innermost core is small and it only contains 33 arms. Add, multiplications, a few other things that are like things you need to build the next most outer core. And then there's another core on top of that that has 137 arms. There's a core outside of that that has 51 arms, and a core with 233 arms, and a core with 77 arms. And in this case, AP is a core that's used to evaluate and build knock expressions, and it's located in like the 5th or 6th core out. And so if I look at its sample, it sees a sample that is much larger than what add sees. Excuse me, a context is much larger than what add sees. So different parts of Hoon will see different things. In user space, everything you do will see your sample, which is the standard library. It's everything. So you won't typically have to worry about this, except that I can't print it simply here because I don't know how long that will take. All right. Now, another part of working with cores is that we want to be able to evaluate expressions like this. Okay, so roll, something I think we played a little bit with roll. Maybe we did, maybe we didn't. But take a look at roll here. What does roll do? It accepts 2 arguments in its sample. One of them is a list of pat UD, and one of them is a gate. And then
It like rolls the gates through the list.
yes, so it basically binary, like pairwise, applies this all the way across to get your values. Right, so it just kind of rolls them together. 10 times 12 times 14 times 16 times 18 gives you that result. Yes. If you wanted to work with a number with a fractional part, so if I were to say .10, this is 10 as a floating point number. It has its own numeric representation, but I could write this with like 10.5. This would be 10.5 if I were to write this on a graphing calculator. That leading dot is to uniquely identify it to the compiler as such. A little bit of a preview. We're going to work with these more later on, but this is 10.5 in a graphing calculator sense, because pat UD are decimal integers, right? I can't talk about like 1.5 in pat UD. It doesn't exist. So I have to use some kind of convention, like a floating point number, a number that I can move around to talk about a number with a fractional part. So this is 10.5. This is 10.5. 10 with a fractional part of 1/2, which resolved as like pat UX or pat UD would be a different number, but there's a special system internally for dealing with this that's common to all systems. And if I were to roll the values together using the characteristic multiplier for floating point values, though this should be a list pat RS. Let me give you this code. It's the old one. Here's the new one. All right. It gives me 0. Now, if I look at mole, let me look at the sample of mole. That's fine. If I look at the sample of mole RS, the sample for multiplication is actually arguably wrong. All right, the behavior is wrong, right? So when I multiply these values, 10 times 12 times 14 times 16 times 18 as floating point values together, I get 0 because it starts from 0. Roll starts from 0. It doesn't start multiplying times 1, it starts multiplying times 0. Think back a couple lessons. Did we have a way of changing the default value? I think we may have talked about this. No, we talked about how to make type unions and all that stuff. I don't think we talked about this yet, because this is where I was going to talk about it. So what we have to do is we have to define a version of mole RS that has a different sample, a different default sample, a different default bunt. Right, the bunt is the default values of a particular type. So we're going to use the buck cab rune. This is a new rune. We haven't run into this one before. The buck cab is going to let us specify different default value for a type. And so in this case, what I'm going to do is I'm going to define a modified multiply that has default values of cab.1 and cab.1. So the default of A and B is 1, not 0. And so if I roll against mmol, if I've modified the gate by changing the subject that I have inside of this gate, now I can correctly calculate 483,840 as my answer in floating point terms instead of unsigned decimal terms. So I can modify gates possibly by wrapping them inside of gates, possibly by doing other kinds of things with them. But what I'm doing is I'm starting to reach in and I'm starting to change things like the sample. Most commonly, I'm going to change the sample. Much less commonly, I will do things with the payload or context because the payload's naturally built and so forth. All right, so Alan asked, why is 0 the default sample for mol RS? The default sample is, honestly, it's probably because almost nothing in Hoon uses floating point multiplication, and so it hasn't been a priority to deal with this problem. And I like it now for pedagogical purposes because it demonstrates this perfectly, like the fact that these are different. To be fully correct at some point, we should probably just fix that, like change it to that point. Now, you make the point that pat RS of 1 is a very small value, and that's because floating point values have their own internal system of representation. This is something I can I love, and I can actually go like super deep into, and I wrote an entire lesson on it on the developer site, so I don't have to do it live. But let me find that. Let me find that guide for you really quick, and it'll go deep into like, here's what's going on with floating point values and why they don't behave the way you would expect. So this is the last lesson of the Hoon School Guide. It doesn't really rely on, well, you should be able to understand this lesson at this point, but it actually diagrams, here's what's going on with this expression and why it doesn't behave the way you would expect. So, all right.
Neil,
So, yes, go ahead.
I have a hopefully quick question. Why does roll need a default value again? So why couldn't roll just be implemented as we need the list to have at least 2 elements, and then you just multiply 10 by 12? Like, use the default because you need to start off multiplying 1 by 10, right? In your example here.
Well, the short answer to that is that it's much easier to tell if a list is empty or contains something than to tell how many things a list contains.
Okay.
Right? Like, is it null is an easy question. How many things are in it is computationally expensive.
Even just saying, does it have at least 2 things?
Yeah, even saying that would be more computationally expensive than just saying, is it null?
Okay.
Now, this is an implementation detail, right? I mean, you could write a version of roll that does that check, and it may even be fast enough to not matter, because I imagine this is jetted and it's running C equivalent of the not code here. Worth experimenting with, but that's why the what we'll call the stock or naive implementation behaves the way it does. It takes the bunt of the first sample of the first variable A, and then it plugs in the first thing from the list as B and starts from there just to get it going. All right, let's see. Okay, so this is cores, right? So cores behave this way. This is the kind of thing they do. All right, now briefly, what are the cores we know about at this point? All right, we know about a bar tis. What else do we know about? What other kinds of cores have we seen? We've seen at least 2 more at this point.
Arson.
All right, it's Barson. All right. One more. What do we call a bar hep? Yep. It's kind of like a loop. They're not always used that way. They do other things as well, but that's sort of what's going on. Now, we talked earlier about sugar syntax and the idea that we can write something like add 1 1, and that what's really happening is an expression like this. Right, that this is really what Hoon sees, in a sense. Now, another interesting thing is that there's actually sugar as runes. Certain runes simplify to other runes. So, for instance, if I were to write an expression like, what's a good way to set this up? I were to write an expression like this. Don't look at this yet because I'm composing this live. All right. So what does a Tisgal do for me? Composes 2 things in reverse order. So I'm actually going to change it to a Tisgar, which composes 2 things together, and then write this code. All right. So let's suppose I have this code right here. All right, these 4 lines. Tisgar, which composes 2 expressions together. The first expression is a Barsen core that has a single arm buck with some Hoon inside of it. And then it ends with the hep hep. And then I evaluate buck. Okay. So what does this let me do? Like if you kind of think about like what is this saying? It's saying define a core with some code inside of it. And then when I say buck, that actually evaluates that code that I had stuck in A equals Hoon, A tis Hoon. Okay. Here's what should start to blow your mind. That is the same thing as bar hep. Bar hep expands to that. It is sugar over that. So when I have an expression in a bar hep, like, what Cole, I can type this correctly. Return index and otherwise sent his buck index increment index. When I say something like this, I glossed over this before, right? With this buck. What this is actually saying is it's saying within the current core, which is this core, which is this core, they're all the same core. Within the current core, modify it by changing the value of index in that core, and then reevaluate the code inside of this Hoon expression, having made that change. Basically, rebuild this arm of my Hoon code, having made that change. All right. This is what cores let you do. We often simplify and write it with things like a bar hep. I sort of toy around with a version of Hoon School where I don't do any sugar at all, and it's all, I guess it's not the one I wanted. Some coal is 5 index. We're assuming index came from somewhere. I am glossing over where index came from. All right. Those two code expressions are the same to Hoon. Keep that Tisgal or Tisgar in sight. All right. Now, what do you not feel comfortable with about this expression right now? I think you probably shouldn't feel comfortable about this yet. But like, what's going on? What's going on when we look at this? So we did use this as kind of a loop before, right? Where, index was defined before. So we'd say tisvaz index 0, and it would like count up to 5, right? In this case, right? Like, this is like stupidly simple code. It doesn't really do anything like useful or intelligent. It just counts to 5. So Daniel Vortex is getting at what should blow your minds here a little bit. So Buck is our default name that we use in the absence of any other specified name, but I can replace Buck with any other lim name. I can change things inside of any lim, and then I can cause it to reevaluate. Sentis is incredibly powerful. It's basically saying, take a lim, take a thing you know about, you know how to access, typically in the current core, and go change something about it, right? Go do brain surgery. Go make it different. Go make it behave differently. Go make it do something else that it didn't do before. So this is really wild. Like, we can actually like just straight up modify gates and stuff. We can just change things that are in our system. Now, we're going to do more of this with what's called a door. And we're going to start playing with doors pretty much now when I'm done talking about this. But this is a fully general design pattern in Hoon. If a core has a name, like an arm in a core has a name, sentis can change the values that are going into that core. A gate is actually doing this as well, right? So I could do a sentis buck against a gate, and there are examples in the Hoon School notes of it doing that. And I can evaluate things that way. Now, this is dense and this is heavy, and this is like the big idea from this lesson about understanding cores, is that cores what lets you do hot reloading of code in Hoon. I can just change part of a core. And depending on the type of core, there are types of cores and things we can apply to it. But for the most generic, fully general core, I can basically do this without limits. I can just change the values that are getting plugged into what's going on here. Okay, so Sam asked, are other languages not like that? So a very powerful language like C, where you can actually just go into memory and sort of change things straight up, like you can do something that would be broadly equivalent to this. But a language like Python or JavaScript, the way that it's treating something like a loop is very different conceptually from what's going on with this. Or this is really saying, so Python, when Python has a loop, it's saying, change the values of everything and then jump back up to the top and run the same code again with the changed values. And while that comes to the same thing, what Hoon is saying is go modify the base code for this arm, the base representation that this arm has available to it, and then reevaluate the arm having made that change. It's subtle, but it's different. So Rashid asks, is buck just a variable limb name, right? So buck is a name. It is the name of the default arm that bar-tiz and bar-hep have, and there's some other core types that have buck as well, but buck is just, if you don't specify a name for some other reason, buck is the default name that the system will give it. And I can define other names. I can give it other names. One example of that, let me see, I thought I had an example earlier. Oh, C. So when I did tis C earlier, when I defined this core, I'm defining a bunch of names that have names other than buck. C doesn't have a buck arm. It could have a buck arm. And if I defined it differently, I could give it a buck arm. But I didn't give it a buck arm in this case. So if I were to try to evaluate buck against C, it would tell me it can't find buck. Incidentally, this is why if you try to evaluate something as Hoon code that is not Hoon code, you get an expression that looks something like it can't find the buck arm. The find buck arm fails. Let me do one. Let me just call this example. So if I were to try to evaluate example one, like if example were, I'm trying to treat example as if it were a gate, it can't find an executable buck arm inside of that gate. That's what senhep is actually doing, is it's looking inside and it's saying, is there a buck arm inside of this core that I was handed? And if there is, I'll evaluate that core. I'll evaluate that arm inside that core. That's what senhep actually does, which is pretty cool. So senhep buck in this case is saying, take the buck arm and effect this list of pairs of changes. And I can specify more changes than this. All right. You will probably have to come back to this idea a few times before you are really comfortable with it. That's okay. It is a deep and powerful idea that touches every single part of what makes Hoon. It emerges naturally from the structure of Nock, although I haven't gotten into the details so much of why that is. But it's because Nock also sort of conceptually organizes things as battery payload, as code and data in the same way. All right. I do want to briefly talk about doors before we get deeper. I can probably skip over paths and file system stuff because I think that's reasonably straightforward to read through, but I do want to talk about cores. So let me talk about doors. A door is a more general gate. All right, so let's say we have we want to evaluate a gate that's ax plus ax squared plus bx plus c, right? So quadratic expression. All right, so we could define a core for this as something like bar-tiz x equals pat ud, a equals pat ud, b equals pat ud, c equals pat ud, and then return. I guess oh well, pasted in the wrong spot. All right, so I could actually say something like this, right? I could define something this way. So let me call this polynomial gate here. All right. And every time I want to evaluate this gate, I have to provide all 4 values to this. So I'd have to say, I want to evaluate x at 1, and I want to give it the values 5, 4, 3. And I have to do this every single time that I want to evaluate this. In the notes, I'm going to give you 3 different ways of solving this problem. One of them is to wrap the gate. One of them is to what's called currying the gate, which is binding some of the values so that they're persistent. We're going to use now what's called a door instead. That's the one because that's the most core-like solution. So that's the one I'm going to use here. And let me scroll down and give you the core code there. All right. Core is a bar cab. It's a bar, which means it's a core. Everything that starts with a bar is a core. So it is a new kind of core. What's different about a bar cab from a bar sen is that the bar cab itself has its own sample. The core has a sample, and then the gates within it, the arms within it, can have their own sample. All right. This is extremely, extremely powerful. Because what this means is that we can use this in two steps. We can use a gate building step to build a particular gate using the values for A, B, and C. So we don't have to specify them every time. And then we can use the gate. All right, so let's see, we have bar cab, and then we're going to use bar cab with sen sig. It's a sen, so it's a function evaluation. We're going to call this door evaluation. Let's page up. All right. So we're going to have door definition and door evaluation. So if I want to define an arm in a door, I would type sig or sen sig, which is sig is the short form, but it's the same thing as sen sig. I give it the name of the arm within the door that I want to use, the name of the door, which in this case is poly, and then the sample that I'm giving to that door. So this is a gate building expression. It's going to build a version of quad that uses the fixed values of A, B, and C. So when I want to evaluate something that, I can evaluate it against the value on the right, which gives me 12, which is the value that I had a moment ago. I can store it, right? So example gate of this, and then I could evaluate it as example gate of 1 or 2 or so forth, and it would evaluate the same way. So doors, which especially you can see right here, bar cab, doors are going to let us build gates on demand subject to certain data. In the next lesson, we are going to start using doors to build some powerful data storage tools, because we'll be able to give it types and values at the top level and then generate arms that do the things we want inside of it. So we're able to push that around. All right. This is really neat. This lets us, so quad is the only arm that we have here. So there's not really like other arms we can invoke here. But in general, excuse me, once we start working with data structures like associative arrays, key value data stores, or sets of values, anything that's more complicated than a list, we are going to use doors to build those and then work with them. All right, so in short, the takeaway right now, the first takeaway is what's going on with the core. It's a cell of battery and payload. And we have a lot of flexibility in modifying the core itself, the code itself, as we are running it. And I guess, the question earlier was, is this different from other languages? One thing that is different is that because of CentIS, we can do this live. We don't have to shut this down and modify the code and then like restart this like we do with the Urbit runtime. The Urbit runtime is written in C. And so if we want to upgrade our Urbit runtime, we have to shut our Urbit ship down and then start it again with the new runtime. If we want to update our Urbit or our apps while we are running them, essentially we are using CentIS to replace the data structures, the executable code inside of that running code directly, and then immediately invoke it. And we get seamless over-the-air updates because of that capability. So that is what cores do. And then we're going to use doors, user space applications, agents, Gall agents, data structures. A lot of other things are doors, because doors are kind of the most general form of a function that Hoon provides. And ultimately, yes, a bar cab does also desugar to a bar sen. All of the bar core runes do have a desugaring to a bar sen equivalent, the way that we saw with bar hep traps a moment ago, but we don't need to get really deep into those right now. Now, the last thing I'm going to show you is Barquette, because Barquette is also a neat one. So let's see. So we have introduced buck cab, defaults, mold value. We have door definition, door evaluation, and then we're going to have Barquette, which is immediate evaluation with arms. All right, so here what I'm doing is I'm calculating the value of the volume of a cylinder with a Barquette. And so it's going to multiply something that's the area of a circle, which is 2 times the height. And a Barquette has a default buck arm that gets evaluated immediately, but it also lets you define subsequent arms that let you help with that calculation, let you simplify it. So area of a circle is a gate that accepts a radius, r, and multiplies r times pi times r. Pi is another arm in this core. Height is an arm in this core. So it calculates volume of cylinder. And the volume of cylinder is actually 125.6637 units cubed in the end. Now, you'll see Barquettes used anytime that you sort of have this kind of compound expression. If you find yourself writing Barquettes a lot, you probably need to just write a library. But when you want to write clear code that does something very specific, Barquettes are excellent for that. But basically, they're just another kind of core that immediately evaluates the same way that a bar hep trap does. Now, Roberts has a question: is there a way to automatically desugar some Hoon? All right, so if we want to see the abstract syntax tree of some Hoon, we can use zaptiz and give it a Hoon expression like add 1, 2. And what it'll do is it'll take the code on the right and maybe Zapcom, not Zaptiz. Zaptiz, I think, goes straight to knock and does something else. Oh, you know what? Zaptiz is a rune that evaluates to knock, but if you give it 2 expressions, you actually evaluate. It doesn't evaluate as Zaptiz. It's not equal to if it's a cell. Yeah, so Zaptiz gives you knock if you give it one thing. Zapcom, which always has tar Hoon as its type, it accepts a type for some reason. It's kind of superfluous, but it's because it's always tar Hoon, the bunt of Hoon. This will give you the abstract syntax tree of the Hoon expression that you have. So this is a send call on a wing named add, a value 1 and a value 2. And, because it's an abstract syntax tree, it's actually what Hoon evaluates. There's some other bits and pieces in there that we don't need to worry about in detail, but Zapcom builds this code for you. Zaptiz builds a particular rune for you. And you'll notice that, Zaptiz of particular values is different than Zaptiz generally, because this is the lookup in the subject. It's finding the value. But here it's saying look up the value and then apply it to the values 1 and 2, and so forth. If you want to desugar the runes, you can. Okay, so the easiest way is to look at the docs, because the docs explicitly document every rune desugaring. So all rune equivalents are written out explicitly in the docs. The second easiest way is to actually open up hoon.hoon and find the rune abstract syntax tree label and look that up. So if I go look up sencol, then it will go find that value for me and tell me exactly like what that converts into. And you have to learn to read what is in Hoon.Hoon, but you can find it out as well. Then there's OpenAP, which I don't remember the exact syntax for. So yeah, maybe it takes a chord string. I'd have to look up what the syntax of OpenAP is, but OpenAP, maybe you ream it first. Anyway, I'd have to look up what OpenAP is. What desugars one layer of runes. This is what's actually used in the compiler. It's the compiler function that does it, but I don't remember the syntax that it expects. And I suspect that yeah, I don't know why it's evaluating to a crash only, because it does more than that. I guess it's getting evaluated probably is what's happening. So anyway, that's what's going on there. So if you want to see the Hoon desugaring, check the docs. That's your easiest, quickest answer at this point, unless you want to delve into the jungle that is Hoon.Hoon. All right. The docs I'm going to give you, they expanded all these cases. They give you a few more examples. We're going to do a lot more with doors next time. So coming out of this lesson, I would not say that doors are your priority to understand. I would say focus on understanding what a core is doing, and in particular, what bar-tiz, bar-hep, and bar-ket look like when they turn into bar-sen expressions. That's where you're going to get the most value in understanding this. Come by office hours. Jack has been doing an excellent job running those, explaining those things for people. Bug me if you see me in the gather house, it's fine. We're happy to talk about this stuff. But this is the big idea. Focus on cores, understand cores, and it will get you through the rest of what's going on with Hoon. All right, that's what we have for tonight.